Hello, everyone. This is Alfredo Abate, your current Chicago Oracle Users Group President. Welcome to today's webinar. As an attendee, you'll be in listen-only mode. You can ask questions in the chat window, which we will monitor. All questions will be answered at the end of the presentation. We'll also be streaming live on our YouTube channel, and the recording will be available there to view shortly after the presentation is finished. It's great to be here with you today virtually, as the group has not met in person since last August. For those that are new to the Chicago Oracle Users Group, we welcome you. Traditionally, our group meets between 4 to 6 times per year in various locations around the Chicagoland suburbs for presentations, as well as hands-on workshops by Oracle experts, ACEs, and authors. With the restrictions in place due to COVID, we decided to go virtual this year to continue to deliver awesome technical content to our members. Today is our 8th webinar in a series of 20 that we'll be holding until November 18th. You can look at our entire schedule on our website. There have been updates made, and you can now register for all the September and October webinars. Please make sure to take a look at those at COUG.us. That's COUG.us. Our user group runs completely unfunded. Our members don't pay any dues, and our meetings have always been free. I'd like to take a moment to thank our sponsor, OAPS Net Partners, for providing the Zoom webinar platform. They are an Oracle Gold partner and systems integrator with specialties in areas of financial business solutions based on Oracle applications, both on premises and in the cloud. They provide services in the areas of AP automation, Apex development, database upgrades, and administration. Next week, don't miss our webinar with Principal Architect from Oracle, Sarah Sumbrum, on From OBIE to OAC, What's Different and What's Gained. You can register for that on our website right now. Today, we are delighted to have Cary Millsap present to us on some things you probably didn't know about Oracle tracing. Cary, welcome. I'm going to give you control of the screen.
Alfredo, thank you very much. Let me share. And rock and roll. I think it looks good. Let me know if it doesn't, please. We good to roll?
Looks good.
Alfredo, thanks very much. And hey, I'll try to remember this at the end, but Alfredo and the whole group there in Chicago, thank you very much for inviting me to speak today. It's a real honor, and I look forward to it. I've got high expectations of myself today, so hopefully everybody will have a little bit of fun. And thank you all in the audience for spending your lunch hour with me. I appreciate it very much. So let's go. I've got only 2 slides I'll show, and I'll go through them very quickly. This is sort of my linearized trajectory through life for the past 3 decades or so. Those of you who know me probably realized that I worked at Oracle for 10 years and a week back in the 90s. And then I started being the entrepreneur. In 1999, I founded a company called Hot Sauce, and in 2008, another company called Method R Corporation. And Method R is still rolling strong today, and that's my next slide. Method R Corporation is just a couple of us. It's Jeff Holt and me. Jeff is the co-author of this book here that maybe you've seen before. We really do 3 things. All 3 of these things really focus on making you faster and making you better. We're developers. We can help you make things go faster. I'll show this QR code at the end, but our URL is simple. It's methodr.com with a hyphen between the D and the R. And that's that. So let's jump into today's lesson. The title of today's show is some things you probably didn't know about tracing. And these are the things we're going to talk about today. Number 1, you really can trace everything. And there are 2 aspects of this. There are probably 2 things that jumped to your mind just now when I said that. I bet you I'm right. Number 1 is, wait, wouldn't that slow everything down if we traced everything? Wouldn't that be preposterous? Wouldn't that kill us? And then number 2 is, why in the world would I want to do that? Well, those are the things I'm going to talk about today. So lesson 1 is, it's okay to trace everything. And I'll start off with a pretty bold statement. That bold statement is this: tracing is unnoticeable if you do it right. And here's my little proof. Application durations naturally fluctuate more than, I'd say, plus or minus 5%. For example, if you had an hour-long report and one day it ran in 63 minutes and the next day it ran in 57 minutes, you're probably not going to change how you talk about that report taking an hour, because 57 minutes and 63 minutes, those are an hour. You might even be generous enough to say if it runs sometimes in 45 minutes and sometimes in an hour 15, you kind of think of it still as an hour-long report. But just about everything you do will fluctuate plus or minus 5%, and nobody will notice. And it turns out that plus or minus 5% is enough to mask the impact of tracing. But I keep saying this, if you do it right thing, and I'm going to get to that in a moment. To finish off this idea here, and give you some reassurance, because this is really what flipped it for me. We have a client that's a very large company, very well-known name. You would recognize their name if I were to say it. And they run an application. They have several applications, actually. One of their mission critical applications, they actually measure very carefully with a product called Dynatrace. And Dynatrace is a user experience measurement tool that allows these guys to know exactly how long the things the users do take. Now, they don't give you detailed Oracle information like I'm going to show you today about what happens in somebody's 57-minute report execution. But they can see that yesterday something took 57 minutes and the same report that ran today at the same time took 59 minutes. They can see the things that happen 100 times per hour that take 1.2 seconds yesterday. If they were to take 1.4 seconds today, they would see that in Dynatrace. And what we've done with this client and others since, but this is the first time that I really felt confident making the statement, is that Dynatrace shows that with tracing turned on and tracing turned off, the response times are indistinguishable. We can't tell which set of response times were generated by a tracing turned on instance and which were generated by a tracing turned off instance. So we have carefully measured this, and it's true. Tracing is unnoticeable if you do it right. But now, what does do it right mean? Well, it's really important to get it right, because you never, ever, ever want anybody to believe, whether it's fair or not, that tracing is hurting your business. So, imagine the scenario where you're tracing today for the very first time. Everybody's very nervous about it. And unbeknownst to you, yesterday, a developer changed a report significantly, changed the source code, went through change control, and yesterday or this morning at midnight, implemented the code change. And the code's not set to run until 10 this morning. It's 9 right now, and you're trying to turn on trace the very first time, and you're very nervous about it. All of a sudden, this report runs that used to take an hour, and now it looks like it's on target to take 4 hours. Well, imagine that the reason it's going to take 4 hours instead of 1 has nothing to do with tracing, but it has everything to do with the code change that the developer made. Well, it doesn't matter. People are going to, because of the coincidence in time nature of these two things happening, we never traced before, and this report never ran for 4 hours before. True or not, people are going to create a cause-effect relationship in their head. And you've got to make sure that this doesn't happen to you, because when it does, the tracing tool gets taken away from you. So doing it right is very, very important, whether it's fair or not. If anybody ever starts to draw a conclusion that tracing is causing something to be slow, they're going to have an uphill battle trying to convince people to let you use the diagnostic data that I'm going to describe today. So what does how do you do it right really mean? And I think the most important thing first is this. And I've got a beautiful picture of Martin Baker Mark 14 ejection seat. The first thing you need to make sure that you have is an emergency procedure for disabling trace immediately. Because if it's your fault or not your fault, if somebody says, hey, this report's taken way longer than normal, you need to pull that little yellow and black cord that's between your knees and get out of the tracing world. If some vendor starts saying, hey, I know what it is, it's this guy turned tracing on. Well, you want to be able to quickly and easily, in a planned, rehearsed way, turn the tracing off. because whether it's fair or not, people will establish this cause-effect relationships in this cause-effect relationship in their head. Number two, my advice to you is certainly respect the IOs per second and size capacity of the storage to which you're writing trace. If you write your trace data to a low capacity device, and you've got high transaction concurrency, for example, then you can possibly overwhelm your device with the writing of trace data. So be sensible, and it's not just the amount of storage that you need, but it's also the pace at which your storage device is able to do writing of the trace data. A quick story about size capacity. How do I know how big a trace file is going to get? Well, as I'll put up here, you can imagine one of the bullet items is going to be, well, you test. Well, one of the things that's very hard to predict without testing is how big are my trace files going to be. But if my trace files are going to be really big and it puts me at risk of filling my diagnostic dest directory, which if you filled your if you fill your diagnostic dest file system, then Oracle won't be able to write to the alert log. And if Oracle can't write to the alert log, your instance is going to hang. And these are the kinds of things you definitely want to avoid. So make sure you respect the IOPS and the size capacity of your storage. Number three, trace at the right level. And I'll give you details about what level means in a moment. And then number four, test. Just like any feature, tracing is a feature. Just like that new invoicing report, just like that new backup program you wrote yesterday. It's a feature, it needs to be tested. It can have side effects that you don't like. So you need to make sure that you know what you're doing. And the way you learn to know what you're doing is by testing. So make sure when you trace things, it's okay to trace things in production, but make sure that you know what you're doing by the time you get there by tracing in non-production environments. It's all about practice. So what is the right level? And fortunately, Oracle gets it perfectly right by how they set their defaults. Basically, start with the defaults. And the defaults are these. And this, by the way, is not DBMS monitor syntax with the PL SQL equal greater than signs. Oh, and by the way, words like wait and bind would be plural in DBMS monitor land, but this is the alter session syntax. So I just use it to save pixels because it's a little more compact than the PL SQL syntax. But the defaults for the three main things that you need to set to turn on tracing are the wait variable needs to be set to true. The bind argument needs to be set to false. I'll explain why in a moment. And the plan stat argument needs to be set to first execution. And as it turns out, these are the defaults, which is great news. Now, using the wrong level can get you into big trouble. And I've got a story about that I'll show you on the next page. So here we go. This is from the book. It's a lot of words. There's really no way around it. I'll summarize it on the next page, but I'm going to read this to you really quickly so you get the gist. A batch program is too slow. With tracing disabled, the program processes 10,000 rows in about 1.2 seconds. However, with wait true, bind true tracing enabled, the same program takes almost 30 seconds to process the same 10,000 rows. This is a 24 times performance penalty, which is horrifying. Now, using wait true, bind false tracing, the same program runs in 1.211 seconds, which is within plus or minus 1% of the trace disabled duration. Notice this number is actually a little smaller than that number. That doesn't mean tracing made it faster. That means that the 5% variance that you'll typically experience by running the same program over and over has eaten the overhead of tracing. So the second paragraph, investigation of the trace reveals that the program's duration is dominated nearly 100% by a complicated update statement. The statement is parsed only once, which is good, but each exec of the statement updates only one row, which of course is the reason the thing's slow to begin with. Now the statement's where clause references 100 placeholders named :B001 all the way up through :B100. With bind tracing disabled, we can tell that each exec call consumes about 122 microseconds, but with bind tracing enabled, each exec call consumes nearly, well, more than 10 times that, 20 times that. It consumes 2 milliseconds. I'm sorry, there's a line break there. That's a very inconvenient break. But for each call, the tracing overhead is 95.8%, which is absolutely, completely unacceptable. So let me summarize the situation. The bind equal false run gives us about 122 microseconds per row. Using bind equal true gives us 2,921 microseconds per row, which ends up being a 95.8% overhead or a 24 times penalty. Now, on the next page, I want to show you the trace data that occurs when you use bind equal false, and the light is going to start to come on for you. So the SQL statement here is in black. I've grayed out things that are necessary but are relevant for this conversation we're having. And here's a statement. It's very famous. It's the Oracle 12c version 12.1 dynamic sampling statement that it uses to figure out whether you are actually using your most optimal execution plans. The hash or the SQL ID for this thing is FRJD8 and some other digits. So you may have actually seen the SQL statement on your system. It uses 3 placeholders. Now, you may be accustomed to calling these bind variables, but they're really placeholders in the SQL to which values are bound in. And when you trace binds with bind equal true, you end up getting a line that says binds with the cursor ID. So you know which SQL statement the binding is happening with. And then for each placeholder, there is a bind section, which consists of a little header, bind pound number, and then 4 lines of stuff, of attributes of that bind, including the value, the data type, and some other things. So for every single placeholder in a SQL statement, every execution will cause this kind of a section to come out. And you can imagine if there were B001 through B100, then there would be 100 of these sections, each of which consists of 1, 2, 3, 4, 5 lines. So when you use bind tracing, you're printing a lot of extra information to the trace file, especially for certain types of applications. And I'll sum that up here. If you have n placeholders, and the example I just showed, n was 3, but in the example in the book, n was 100. Well, bind equal true will write 5 times that number plus 1 lines per exec call, and the plus 1 comes from this line here. So 5 lines per placeholder gives us 5n plus 1. Now, as it turns out, the way that the Oracle kernel is written, for portability reasons, Oracle makes 2 write calls for every line of trace data that gets emitted. So it's actually making 2 times 5n plus 1 write calls. So if n is 100, then 5n plus 1 is 501, and 2 times that is 1002. So for every execution, Oracle would be making 1002 write calls to the trace device. And if your application makes way too many exec calls, for example, 1 per row, then the weight of these write calls is going to suffocate your app. So the solution's really simple, as it turns out. Trace with weight equal true, bind equal false. Just always go in with bind equal false. With the data that you would collect using weight equal true, bind equal false, you will have enough information to know whether the application makes way too many exec calls. If the application does make way too many exec calls, then fix it. Do the thing that's been advised ever since Tom Kiden before, which is process data in sets, not in individual rows. When you do this, not only will the application be faster, but now it will be safe to trace that program with weight equal true, bind equal true. Now, why would we want to use bind equal true? Well, because sometimes the value that gets passed into the SQL has a dramatic impact on how long that execution of the SQL consumes. For example, imagine a big for loop in PL/SQL where you're looping through accounts at the end of the month or something. And imagine that you're trying to close 100 different accounts, but account number 13 happens to consume 80% of the total time consumed by that loop. Well, the first thing you're going to want to know is, well, which values get bound into the SQL in loop iteration number 13? Because that's what I want to diagnose and figure out and fix, right? The other 99 values in the loop are not as important to me as the 13th one. So that's when I want to see the bind values, but I don't need to see them in my first iteration of analysis because it's not safe. We've done the trace weight equal true, bind equal true, and in probably 9 cases out of 10, maybe 29 cases out of 30, nobody ever notices a difference. But if your application does this row by row processing thing, and if it uses a lot of bind variables, then setting bind equal to true will cause a performance problem that will cause people to be nervous about tracing from there on. All right. So don't use bind equal true until you know it's safe. And you can find out whether it's safe by using bind equal false. Now, in the book, I go for an equal amount of time that I've just spent talking, telling another story about how if you set plan stat to all executions, you run the same kind of a risk. Plan stat defines how frequently the Oracle kernel will write your execution plan to your trace file. Now, the default is first execution, which means that whenever a SQL statement is executed for the first time, that's when Oracle writes the execution plan out to the trace file, and it won't write another execution plan for that cursor and for the life of that cursor until it's closed and reopened. So that's usually okay because all we want to see is the plan that this statement uses in our trace data. But sometimes maybe you get an application that changes execution plans from one execution to another. Or maybe what you think you want is a list of all the execution plans and their costs and their amount of LAO processing that they've done, the number of reads they've done. Maybe for some reason you want that information. But what I recommend that you not do is set plan stat equal to all executions until after you've tested it. Because the problem is, imagine that your SQL statement's pretty complicated and your execution plan is 1,000 lines. It's 1,000 distinct row source operations. Well, if you've got the row by row processing exact, like I just talked about in the other example, then you're going to end up having 1,000 lines written to the trace file every single time you insert a row or update a row in the story that was in the book. Well, you don't want 1,000 lines, which by the way, takes 2,000 write calls because of the way Oracle is factored. You don't want those in the way of your application. So very analogous to the bind equal false advice, I compel you hopefully to use plan stat equal first execution. So to recap, I've given you quite a few details, but the two that I really want you to remember are: number one, make sure you have an eject procedure that's tested and ready to go. And anytime anybody goes, I think it's tracing, pull that handle, and there's no way that anybody will be able to blame tracing after that. The effect of turning tracing off, by the way, is instantaneous. So when I do a dbms monitor.database tracing disable, it's going to happen right there. And it's just a matter of calling it without having to spend 45 seconds looking stuff up and typing it. You need to have this at your fingertips to make sure that tracing doesn't get blamed for something that's not tracing's fault. And then number two, test. Testing will actually teach you need an eject procedure, but I want to make sure that I mention it explicitly because the eject procedure is very important, both in terms of you may need it and in terms of it just gives you more confidence to know that if you have to turn this thing off, you can in an instant. And that's lesson one. That is the know what you can really do this. You really can trace everything. Lesson two, and I think this is much more interesting, is why in the world would you want to? And here we go. It starts with this. Ash and AWR, Active Session History and the Automatic Workload Repository, are great, of course, if you're licensed to use them. But there are things that you can do with trace data that you cannot do any other way. And you probably want to know, well, what's so special then about tracing? And it comes down to two things. Number one is you get call by call detail. Every single database call the database makes, every single operating system call that the database makes gets a line written to the trace file. And number two, you can group by user experience. Okay, so detail, user experience, so what? And by the way, if it didn't make that much sense, what I meant by user experience, it'll become clear as I keep going. So detail, user experience, so what? Well, with tracing, with detail and a user experience orientation, you can answer 4 vital questions. These questions sound so simple, but almost every DBA that I've ever met is conditioned not to ask these questions because they know they can't answer them with Ash and AWR. Number one is the real simple, how long does it take to run that? Now think about this for a minute. Who would give you information about how long something takes to run? And the answer is usually the person who runs it, right? The person who books an order goes, you know what? Normally it's sub-second, but that last time I booked an order, it took 17 seconds. I watched, it's happened enough that I'm starting to look at my watch now when I do this. Or maybe better yet, you've got an application that every time you do something that needs to be fast, it says, I just did that and it took 13 seconds right on the screen. Right? If you care about performance, then you probably have already started integrating little things like that into your app where people can see how long things take. But how would I go to my $V tables or my X tables or an AWR report or my ASH data and find out how long it took that person to book an order? And the answer is you really can't. I mean, you can approximate it. There are numerous techniques executed by brilliant people. Tanel Potter is one person I've got in mind that can get you close to being able to know how long did that book order take. But the data don't give you a grouping handle that allows you to answer this question with the stuff that people traditionally look at. But the first thing I need to know is how long does that thing that's hurting your business take to run? The next thing I want to ask is why? Why does it take so long? And I don't want the answer in the form of, well, when I book an order, I notice that overall CPU utilization is 73.4%. That doesn't help me. What I need to know is your thing took 13 seconds. Where did that 13 seconds go? That specific 13 seconds, nothing else, and I want nothing left out. I want to know exactly where that user's 13 seconds went. If I have that information, then I can do the next question, which is what if? Well, what if we make the application so that it doesn't do so many read calls? How long would it take then? Well, if I know how long it takes doing read calls before the fix, and I can make a prediction about how many read calls I can eliminate, suddenly I'm able to predict, hey, if we get rid of read calls, how much faster will this be? And in my line of business, I see all the time people going, yeah, we need a new SAN. Why do you need a new SAN? Well, we need a new SAN because the aircraft maintenance reports, they're supposed to come out in 10 minutes are coming out in 15. And I think if we get a faster disk, it's going to make them faster. Well, have you looked at, you told me how long they take. They take 15 minutes, but why do they take 15 minutes? I don't know, but our disk is really busy while they run. Well, it's not necessarily disk that's causing your maintenance reports to be slow. Let's see where your maintenance reports spend time. And if they don't spend time on the disk, then we're not going to let you buy a new disk because you're going to be ticked off if you spend that money expecting maintenance reports to go faster and they're not. So this what if question is vital. It's absolutely vital because without being able to answer this, everything becomes trial and error. Well, I don't know. Let's buy it and see. Oh my God, seriously. Is there a return policy? Can you get the hours back that you're going to take from your budget, for the people it takes to put this thing in and connect everything to it? Are you seriously, you're just going to try it? And if it doesn't work, you're going to figure it out then? The ability to answer what if gives you immense power compared to the whole trial and error universe. And then finally is our loop iterator, the what else question. Sometimes the first iteration of analysis gives us a big improvement, but we use the same measuring tools, trace it again. Hey, there's even more we can do here. So the question, what else can I do to make this thing that we're looking at faster, sometimes evolves into, you know what, we're done. The only thing we could do to make this faster is really more expensive than it's worth. So we're finished. We have economically optimized this particular program because the what ifs all result in, yeah, we could do that, but it's really not worth doing that. There's not enough bang for the buck. So the what else might be, can I do anything else to the program we're looking at now? Or the what else question could be, is there another program we should be looking at instead? Because now that it's fixed, maybe there's something else that's risen to the top of the urgency list. So the cool thing is that answering these 4 questions makes you look like magic. It really does, because it allows you to see into the future. It allows you to stop people from making decisions that are destined to fail. So what kinds of things can you do with trace files? And I'm just going to list a big old blob. This is not all you can do with trace files, but these are some of the things you could do with trace files. And I'm going to talk about 4 of them in detail. And in fact, these 4. So let me just tell you what these 4 are real quick. So Number one, with trace files, we can see exactly where your time has gone. So this enables us to answer the how long and what if questions. I'm sorry, how long and why questions. Predicting the impact of a proposed change. I just mentioned it, but I want to show you an example of it. The third blue one, diagnosing performance problems, even really tricky ones. I've got a cool story I'm going to show you. And then number four, the ability to draw a Gantt chart of how your workload fits together. You probably never thought about even like, is that a thing before? And I'm going to leave you hanging on that. That's going to be the last story I tell, but we're going to get to it in about 15 minutes. So these are the four things that I'm going to highlight in the few stories that I'm going to tell you coming up. So number one, let's talk about predicting the impact of a proposed change. So let me start with a program from the Oracle payroll application called PYUGEN. PYUGEN is a batch job, again, part of the Oracle prepackaged payroll application set, part of Oracle eBusiness. And the first question of our four, how long, why, what if, what else, is how long? And from this table, basically what you're looking at here is a summarization of trace lines that groups by what I'm calling subroutine. But what a subroutine is, you can tell. It's the CPU statistic on database call lines like fetch, parse, and exec. And it's the ELA value, the elapsed duration, that's displayed on wait lines that have names like SQLnet message from client and latch free and log file sync. So this is basically just an aggregation that says there were 95,161 lines in the trace file whose that were waits, whose names were SQLnet message from client, and the total amount of time adds up to 984.010 seconds. And if I divide that into the total, I end up knowing that that's 49.6% of our total time. And if I divide this by the call count, then I end up with a mean duration per call statistic that I can use in my analysis. But the question is, how long did this user experience take? And if we collected our trace data properly, which I did, then the final row of this table is the answer to the how long question. This thing took roughly half an hour. 1900 seconds is roughly half of 3,600 seconds. So the how long question is trivial. We know exactly how long this took. It took 1,985.2 seconds. The second question in the list of four is why. Why did PYUGEN take the time it did? And we can see that answer in this format as well. The number one reason it took 1,900 seconds is because it spent 984 seconds doing this thing called SQLnet message from client. The number two reason is it spent 20% of its time, 418 additional seconds, executing this subroutine called SQLnet more data from client. So that's interesting. Now let's start asking what if questions. And the first what if question might surprise you because nothing I've shown you so far would lead you to ask the question that I'm getting ready to ask. But here's the question the client was asking when we got to their site. What if we get rid of latch free? Was the hypothesis that this client was working on really hard for months before we arrived. This PYUGEN thing, it's not made up. This was at a company whose payroll was supposed to be paid out on Fridays, but because PYUGEN was so slow, they weren't able to pay payroll on time. Well, because people weren't getting paid on time, they were coming in on the weekends and vandalizing the company property in protest for not getting paid on time. So this was a serious business problem for these guys. And they spent lots of money on diagnostic tools and so forth. And one of the tools that they were looking at was a dashboard that shows on the system right now, while payroll is running and while everything else on the system is running, what is the number one wait event on the system? And the number one wait event on their system was latch free. Now it's crazy. We trace payroll and we find out that latch free is only a 1.2% contributor to the duration of payroll. But we can now answer the question, what if we were to eliminate latch free from payroll? And the answer is it wouldn't make a bit of difference because nobody's going to notice 23 seconds on a half hour. A half hour minus 23 seconds is still a half hour. So getting rid of latch free is clearly not the play here. The play is SQLnet message from client. Now this is funny too, because the very first thing when we showed the DBA this report, he looked sadly at his shoes and he just sort of shook his head. And we're like, why so sad? He goes, well, because that's an idle event. And we know what that means, right? Oracle teaches people that you're supposed to ignore idle events. So if we ignore that, there's really nothing else left to do. Oh, there's SQLnet. No, that's an idle event too. And then there's, what's this other thing? Unaccounted for. There's nothing here for me. I can't optimize anything because if I ignore that, I get down to DB file sequential read, and goodness, guys, I can't double throughput by changing this because it only contributes 14% of our time. If we eliminate DB file sequential reads, nobody's going to notice that either. A couple 100 seconds short of a half hour is still nearly half an hour. So the DBA looked at his shoes, and Jeff and I were ecstatic. We're like, no. This thing right here is your problem. If you want throughput to double, if we could somehow get rid of this, then we'd be in the sugar land, where we want to be. So Jeff is the one that noticed this 10 millisecond average duration per call. The picture that they drew when we first got to the site was of a computer in their IT department that had Oracle running on it. So Oracle is running on the computer and the application is running on the same computer where the Oracle database is running. This is a pretty standard implementation of Oracle eBusiness. Well, knowing that PYUGEN was running on the same box as the Oracle database, Jeff saw this number here and thought, why in the world would you be getting 10 millisecond latencies, 0.01 second latencies between two programs that are on the same piece of hardware? And so we went and looked at their TNS names.ora file to figure out, what alias are they using? How are they connecting PYUGEN to the database? And what we found out was they had used a protocol adapter of TCP for everything that connects to the database. And we said, hey, you've only got one protocol adapter. They go, yeah, you can only have one, right? We go, no, you can actually have several. Oh, I didn't know that. And we said, yeah, so what you want is the people on the 14th floor, they're going to have to connect through TCP IP because they're not on the server. But PYUGEN and all the other bash jobs you run, they can direct connect to the database using the IPC protocol adapter, for example. And let's do that. Let's create another connection string that uses IPC, and we'll race them. We'll write a little PL/SQL procedure that makes a boatload of network IOs, and we'll race them and see how much faster it would be to use IPC instead of TCP. We did that and figured out it's about 55 times faster to make a network IO through the IPC protocol adapter on this system than it is to use the TCP protocol adapter. So our what if was, well, what if we can reduce this latency from 0.01 to a number that's 55 times faster than that? And the answer is, well, it'll make this number about 55 times smaller. And we can do that arithmetic in our heads. 984 is about 1,000 and 55 is about 50. 1,000 divided by 50 is 20. So I'm thinking we can make 984 seconds, nearly 1,000, change into 20 seconds. And if this number changes to 20, then this 1985 is going to become roughly 1,000. It's going to be about half. And that's not even to mention that maybe we're going to have an impact on the second line too. The first line was enough to go, yes, we have to try that. And they did. They of course, they had to go through change control procedures that happened after we were there. But about 3 days later, we got a phone call from them. They called us and said, yep, throughput doubled. Everything's cool. People aren't tearing up the place anymore. We're sending paychecks on time. So we didn't get a chance to do the what else. There might have been something else we could have done. We didn't get a chance. They got to their goal and they finished the project in their minds. So asking how long, why, what if, got us to the end of a process that had taken them 3 months, and they were never going to get anywhere by trying to hammer on getting rid of latch free and payroll. And we did the analysis in roughly an hour. It was actually a little less than an hour. So that's story number one. Story number two, I'm not going to tell the whole thing, but let me just ask you. Here is a list of SQL statements that comprise a 110-second user experience. A user sat down and clicked a button, and I'll tell you what they were doing. They were trying to search for cheese from their inventory of food ingredients, because this is a test kitchen in which a chef is trying to invent the next sandwich, the next brownie, the next coffee. So the chef says, I want to know how many different kinds of cheese we have. 110 seconds later, the application responds, here are all the cheese that are in stock. 110 seconds is so long that a person loses his train of thought during the process of waiting for the answer. Oh yeah, what was it again? I was trying to, oh yeah, I was looking for cheese. Okay. 110 seconds was absolutely unacceptable. And the unacceptableness was exacerbated by the fact that this is running on a $6 million Oracle Exadata machine. So it was a problem. So we figured out, hey, 88% of this 110 seconds is being spent executing this query, frjd8, the same one I showed you a while ago with the 3 bind variables. We can turn this off. We can turn it off by altering the session to turn off the optimizer or adaptive feature thing that causes this dynamic sampling SQL statement to fire. So my question to you, and I know I can't hear you because we're on Zoom, but if we were in a room together, I would ask the room, if we get rid of 97.6 seconds out of 110, how many would we expect to be left? And you could do the arithmetic in your head. 110 minus roughly 98 is about 12. So I would expect you to say, I think if we eliminate the red SQL statement, this thing should run in 12 seconds instead of 110. And guess what? It did. It's just usually just that simple. We get rid of that red statement. It's no longer here. There is no more select executions under fetch count. It doesn't exist anymore. It's not in there either. And now what comes to the top is select GSM formula output type. There it is. Select GSM material type. There it is. Select thumbnail. There it is. So what we've got now is application statements at the top of the list of things that take time. And that's exactly what we want. We want our computer doing work only that we care about, not work that's sort of ancillary that we don't want in our way. So just making that one change made searching for cheese go from 110 seconds down to 11.6 seconds. And 11.6 is a lot better than 110, but what else could we do? We did the how long, we did the why, we did the what if. Now let's do the what else. Well, here is another way. It's similar to the way that I showed the PYUGEN data of summarizing the trace data. And what we see is that out of the 11.6 seconds, we're spending 7.8 of it parsing. Well, this is an anti-pattern that hopefully everybody on the call knows. You should never, ever have a user experience whose total duration is dominated by doing parse calls. When have you ever written an application where the user said, hey, I love your app, but man, can you make it do more parsing of SQL? Right? No. Parsing of SQL is something that you have to do. It's not something that you want to do. So the less you can do of it, the better. And why in the world does searching for cheese need me to do 881 parse calls? So there's something fishy here. Something's wrong. Let me show you another way. And this is not a third way. It's just the other way that I showed you a minute ago. This is the same report that I showed a couple slides ago, except I'm just showing more stuff off to the right. And it all comes from the trace file. This particular query, select GSM material type, executes 437 times. It has 437 distinct texts. If we were to look at the statement, which I'm not going to do in the slides here, but if we were to look at it, we would see that in the where clause, there's buried a where ID equals, and there's a string buried in the SQL statement, which is basically dynamically generated by the application. And this statement runs inside a loop 437 times. And every time the statement runs, it gets a different literal value plugged in. And so that's why there are 437 distinct texts. That's why there are 437 executions. And that is why there have to be 437 parse calls for this one statement that should have been shared but wasn't. Same story here, 437, same loop. Now, isn't this cool? Notice that number there. This query, select thumbnail, spec number, spec name, etc., returns 437 rows. Well, now we're starting to get an insight into how this application is designed. This thing actually returns IDs that get plugged into these two SQL statements that run in a loop for every row returned by this guy, which executes once. There are 437 rows returned. These two statements execute inside of a loop. So we can see the app start to form its shape in our minds by looking at trace data. And we actually, let me see, I'm looking at my next slide. Yeah, I want to make sure I know what I'm talking about here. We actually got permission from this client to rewrite the search for cheese function. And we were able to get rid of the parsing, the unnecessary parse calls. And we ended up with this profile. Instead of running in 11.6 seconds, now we have a search for cheese that runs in 0.8 seconds. And this is on a slower test machine. It wasn't the $6 million Exadata. So searching for cheese now with the changes that we have proposed would be a sub-second experience. Now, of course, Oracle wrote the app. Actually, that's false. Oracle bought the company that wrote the app about 2 decades ago. And we suggested to Oracle that if you were to rewrite your app this way, and by the way, here's the code, it would return the correct answer and take less than a second instead of on the order of 10 seconds. And it would help all your customers. I don't think they've implemented it, but this is the best I know to do with a vendor, is to be able to say, look, here's a problem. Here's a solution. We've tested it. It works. You have to test it, of course, before you integrate into the product. But here's how much time it'll save all your customers. Thank you very much. So that's the end of that one. And again, we got here by asking how long, why, what if, what else. All right, let me tell the second story, and then I'll recap. I'm looking at my time here. Yeah, it's going to be tight. We may end up having not very much time left over for questions, but Alfredo told me that I can take a little extra time to answer questions if you guys are interested. So I don't have a hard stop. We're good to go. So this one is a story about diagnosing a particularly tricky intermittent performance problem. And here's what the problem was. It was actually airport management software that does things like tells you what gate to go to, which baggage claim to go to, what flight, 762, whether it's on time or whether it's late, whether they build the gate for it or not. This application actually made database calls. Again, 100,000 transactions per hour is typical. And anytime the application would request data from the database that didn't make it back within 5 seconds, the application would time out. And there would be roughly 10 timeouts per hour. Now, this sounds pretty good because that's a 99.99% success rate. And that sounds great, but 10 timeouts per hour is unacceptable, because 10 times that a bag goes to the wrong baggage claim, or God forbid, maybe to the wrong city, these are costly timeouts. So just because we have 4 nines worth of greatness doesn't mean that we're happy. It's unacceptable that there are 10 timeouts per hour. So that's the problem as it was stated to us. And it's a classic problem of we've got lots and lots and lots of happy, but we have a little bit of not happy, and we've got to find it and get rid of it. So here's what we did. We asked the client, and it was actually the client's customer that we had to ask, because our client was the software vendor. Their customer was the airport. So we asked our client to ask their customer to please trace everything. And it was connection pooling for about an hour. And they did that. Now, it took a week or two for them to get approval to do it. And they were afraid, and, won't it slow everything down? And we went through the whole spiel of why it won't, and we're confident, and make sure you got an injection handle. Everything went swimmingly. For an hour they traced. They turned trace off after an hour, and then they're like, all right, what do you want me to do with the data? Well, how much data do you have? Well, we've got 67 files, roughly 5 million lines of trace data. So they zipped it, gave it to us. It's not that much data. It's I don't know, 20 megs or 50 megs or something like that. Wasn't that hard for them to get the data to us. What we saw in the data, what they told us about the data, rather, is that they did about 90,000 transactions. There were only 5 timeouts, which is good. I mean, normally if they're expecting 10 timeouts in an hour, they did better than that today. So I'm glad they didn't have 10, but I'm glad they had more than 0, because if they'd had 0, then we'd have to trace again and try to catch it in the act some other time. So 5 is a really great number to have here. And they told us one of the transactions, horrors, lasted 9.5 seconds. All right, remember the timeout is 5 seconds. So one transaction lasted nearly twice the timeout interval. Now, what I'm getting ready to show you takes less than 5 minutes to do with the right tools. And I've got a video at our website that'll show you the details of how to do this if you have this particular tool. But I'm going to tell you how to do it by hand in case you don't have the tool. So here we go. There were 89,000, they said roughly 90. There were exactly 89,079 user experiences in these 67 files. Now, how do I know that? I have a tool. We sell this tool for a living. But in the trace files, and you'll notice that the group expression here in column 1 consists of a file name, a colon, and then what we're calling an island ID. But what's really going on here is that this file, GXL aura 131.168.trc, beginning at line number 145010, has a user experience that lasted 9.4 seconds. Now, when I saw this number, I stood up and threw my hands up in the air like I just scored the winning touchdown, because this is exactly what they said they saw. They had 5 timeouts, count them, 1, 2, 3, 4, 5, that took longer than 5 seconds, and I found them all. I know exactly what line and what file these things occur on. And the way that I know, the way the tool works, if you Google for this, and I've got it in a note here in a couple more slides, but I used an algorithm called the Oceans, Islands, Rivers algorithm. And if you Google Oceans, Islands, Rivers, Millsap, you'll find it. But essentially, the algorithm works by noticing that in a connection pool, user experiences tend to be delimited by longish duration SQLnet message from client calls. So if you can find a threshold for what longish means as a number, you can actually go through and say, okay, there's a longish SQLnet message from client, and then there's like 50 calls to, database calls, and there's even little short SQLnet message from clients inside of this island of activity. But then here's another longish SQLnet message from clients. So the long ones we call oceans. The activity in between the oceans we call an island, but islands can have rivers. And these rivers are these SQLnet messages from clients that are these quickie little round trips between the user and the database that are part of the user's experience. So Oceans, Islands, Rivers algorithm is where this data comes from, but it just comes straight from the trace data. So we know which file it is that contains the experience that we're interested in. And I'm going to change pages, and it's not going to change much, but I want you to notice that this is multiple files here. If I just look at the one file, this 131168 file, and run the same command, I can see that there was only one timeout file. But the problem is this file contains 4,822 distinct experiences, and I only care about this one. So what I can do, either with a tool or by hand, is I can chop out the trace data. You can see it's only 8 calls. It's not that much trace data that I need to go chop out, but it's a little tricky chopping it out for reasons I'll tell you in just a second. But when I do, I can actually run whatever tool I want. And again, this is our tool, but you can run any tool that you want, TK-Prof even, and see the details of where this 9.47 seconds went. And on this engagement, it only took us, 10 minutes, less than that now, which you see on the video that I'll give you the URL for in a couple of minutes. But it took like 10 minutes to figure out, oh, your application's suffering from a row lock. And they said, oh, you know what? Our AWR reports don't mention that. I'm like, well, no wonder, because you've got 8,000, you've got 89,000 experiences, 89,079 experiences. They're all doing all kinds of things, consuming thousands of seconds, right? An hour across 67 files is like 67 hours worth of data. And you probably only have like a half a dozen of these lock contention things, and they're probably taking 5 to 10 seconds a piece. So no respectable AWR is going to go, ooh, it's locks, right? Because locks are going to be like 0.007% of the time spent. But they happen to be 100% of the reason that this particular execution that we caught timed out. And it was funny. We found a combination. Not all 5 of the top timeouts were row lock blocked. 2 or 3 of them were log file sync blocked, like this one almost is. And a couple of them were blocked by read calls, which actually ends up being the reason for the row lock contention. So it was amazing. In like a half a day, we had 67 files at our feet, when we were able to tell all these different interrelationships and things about their data. Now, to get a report like this, basically to chop out a trace file, to isolate the trace data by hand, one, you need to know about the oceans, islands, rivers algorithm, which I mentioned before. And then two, inside of a trace file, there are these lines labeled parsing and cursor that may occur before the first line in the user experience, but you need to include that in the trace file output that you chop out by hand. And then sometimes after the last thing the user experiences, deeper in the trace file, there may be some execution plan information. You need to include all the stuff that needs to be in the trace file that doesn't necessarily happen between when the user clicks and when the user gets the answer back. And I'm perfectly happy if you like this option better, you can use the method R workbench, which is the tool that I've used to show you these examples. And if you're interested in that, take a quick shot of this QR code and it'll take you to our webpage where there's a video. It's 4 minutes and 57 seconds of the steps you would take to actually do this using a tool. Now, I promised you the Gantt chart thing, and I've only got one slide, but it's kind of a lingerer. I'll show you this and talk about it for a couple of minutes. If we trace everything, then we have trace files that inside the files have information about what time the thing they measure began and what time the thing they measure ended. And if we know that, we can actually export that begin and end data to Excel, and we can make a graph that looks like this. And the way to do it, this will be in the video, so I'm not going to go into super amount of detail, but basically, if you know the start time and the duration, then you make a stacked bar chart with an invisible bar, the duration of the start time. So basically, we're seeing an invisible bar here before this bar starts, and then the start time of that trace file and the duration end up making up the blue part of the bar. So these are the instructions for how to get Excel to do that. The main thing that we're seeing here is that, hey, something starts and takes quite a while. Let me actually page up so that's not in the way. Something starts and takes quite a while. Likely what's going on is this thing kicks off some stuff and then sits there blocked on a SQLnet message from client, some other stuff finishes, and then it resumes its activity and finishes off. These guys were interested in making sure that this workflow finished about an hour or two earlier than it was, because it was penetrating into their day's work. And one of the things that we found that was interesting was there is nothing going on when that program completes until that little fast program starts. And we could look in the trace file and see what's the last thing this trace file shows, what's the last SQL statement that got executed, and what's the first SQL statement that this guy shows being executed. And then we can go to the client and say, hey, do you know what in the application happens between when you run this SQL and when you run that SQL? And we got really lucky because they knew their application really well. And they go, oh yeah, we always wondered if that was a problem, what the app was doing. And then we can see in Technicolor, yeah, that is a critical path thing. We could reduce the total duration of our batch work by this duration from that arrow to that arrow if we go look at the application and tune this up. And it turned out to be an easy thing to do. It was actually like number 35 on their list of things that they might try someday. But we were able to show them that no, honestly, is not the 35th thing you should do. It's actually the thing you should do right now. And a repeat of that process caused them to basically be able to fit their batch window into, I think I got it down to like 4 a.m. is when this thing finally finished. So it was an application problem, not a database problem, but we diagnosed it using Oracle database trace data, which I think is just magic. Now it's 1, and I'm technically out of time. I'm going to do this like breathless recap. And Alfredo, I don't see any, I can see the chat window and I don't see any questions. So I'm going to do a recap real quick. And then if you have anything else you want to do or say, I'll let you do it. But I'm going to take maybe 3 to 5 minutes here if I can. So number 1, even if you don't need to trace everything, knowing that you could is kind of a superpower. Why? Well, because you can do things with trace data that you can't do any other way. You can see exactly where people's time is gone. I've shown that in 3 different examples. You can predict the impact of a proposed change, right? There's no more war room where people are thinking, yeah, if we can just buy another disk, maybe that'll help. Well, you'll know it will help this program this much. It will help that program that much. Do you still want to buy it? It allows you to measure, test your system the way your users feel it. I can't tell you how many times I've seen people do like before and after a 12C to 18C upgrade test. And how do they do the test? Well, maybe they'll use the real application testing suite from Oracle, which is awesome, but it's kind of costly. And they'll like catch the workload before the upgrade, and then they'll stage their upgrade, and then they'll run the same stuff, and then they'll look at Ash and AWR on both sides. The problem with looking at Ash and AWR on both sides is you're not actually looking at the that might cause people pain later. You might see, yeah, utilization was 60% before, it's 48% after. That's got to be good, right? Well, who the hell knows? Does invoicing run just as fast as it used to? Does book and order run just as fast as it used to? And if you think about it, there are ways that no matter what Ash and AWR say, unless you're looking right at book and order, pick and order, ship and order, bill for an order, you can't know how long those things take. But with trace data, you can. You can know exactly how long they take, and you can know exactly why they take that long. We talked about this one, even the intermittent stuff. If you just trace everything for a while, you're going to catch it too. I really love the wording of this, becoming intimate with the performance of your key application functions. Ladies and gentlemen, if you sell baseball caps for a living, then you need to know how long does it take to book a baseball cap order, to pick it, to ship it, and to bill for it. And you need to know, if I double the number of orders in a month, what's it going to do to my system? If this disk gets really busy, what's it going to do to the response time of booking an order? You need to know that stuff before it hits you between the eyes, or more likely in the back of the head, because you don't see it coming. I showed you how you can draw a Gantt chart of how your workload fits together. And one thing I like to mention is it can drive code reviews between your developers and DBAs. Most people have silos of database administrators and separate silos of application developers, and they rarely talk. And sometimes the teams are antagonistic towards one another. The DBAs think that developers are just making problems, and the developers think the DBAs are just being, I don't know, too picky. I don't know. But if you sit down over a profile that shows how your time gets spent over some trace data, you can actually have developers learn by feedback of, oh, that's why I don't want to do row by row processing. I see now. Oh, I don't want to call the user PL/SQL variable. I want to call the sys_context PL/SQL function, because it's way faster than the user PL/SQL variable. And I can prove it. I can trace this. I can trace that. I can show you why this one's faster than that one. There's no opinions. There's no arguing. It's just flat based on data. So it's a great document, or trace files are the right data to drive conversations between developers and DBAs. And finally, it enables you to plan how much capacity you'll need. And that's another hour-long program. Maybe when you do 21 for 2021 next year, you can have me back and I can do that one for you. But it enables you to actually have the type of detail that you need to be able to see, when am I going to need to buy more service credits? When am I going to need to upgrade my CPU? Real quickly, if you liked what I talked about today, there's loads more stuff like this at methodr.com. In particular, there's a performance monograph series that I've started. I think there are 4 documents in it, maybe 5 by now, but these are the first 4. And if you just go to methodr.com and type monograph into the search bar, you'll find them. But I think they're pretty interesting. They're just 1 page, front and back, so they're not a big reading assignment. But if you're interested, I think you'll enjoy. I think you'll enjoy reading them. I'll leave you with my business card. This is how you contact me. info@methodr gets me directly. Of course, Twitter, methodr, and there's a QR code if you want to take a snapshot on your phone and go visit what we've got. The website's actually all new. We put up a new website about 4 days ago. So if you have WordPress questions for me, I'm particularly well attuned to WordPress at this moment in time. Alfredo, I've talked and talked and talked and talked and talked. Somebody asked, how would this method change when using dedicated connections versus pooled connections? And the answer is, it would get easier, because instead of one trace file, here, I'll show you. Instead of one trace file containing 4,900 things, each trace file would have just one thing in it. So it would save a step. I wouldn't have to go from here to here, because one file would only have one user experience inside of it. That's it. Alfredo, hearing your voice would make me very comfortable at this point.
Hi there. Yeah, great. Awesome presentation.
Oh, thank you very much.
Thank you so much for coming on today and doing this. Like I had mentioned to you before, we started the broadcast with the COUG has been waiting a long time to try to get you to come out, and this was a perfect opportunity with no traveling, and
Yeah.
we're very, very grateful to have you and hope to have you in the future, maybe even in person. We'll see.
Awesome.
Yeah, I think the only thing is just want to mention real quick. Okay, here's another question that came up.
Yeah.
Free version of Method R to try.
Yeah, we have a trial license. If you go to our website, let me show you real quick. Let's see if I can get a, no, actually, I'm going to pull a tab off of here real quick. If you go to method-r.com, the very first page talks about our workbench. There's a learn more free trial button. There's also a software free trial drop down. If you click that, you'll get a trial license that lasts a couple of weeks. It will allow you to operate upon the sample data that we ship with the product. So it won't let you use the features on your own problem, but it will allow you to use all the features and see what the tool does. I think the rest is just very kind thank yous and cool. Thanks,
Awesome.
Ramesh.
Well, thanks. Yeah. So just two things real quick. This broadcast will be available on YouTube right now. It'll still say live for a little while, and then eventually it'll go away, but it'll just be a video on our Chicago Oracle users group channel. And then next week we have Sarah Sumbrum on what did she have? She has a OBIE to OAC, what's different and what's gained. But also you can check out the rest of our September and October schedule, which is now available for everyone to register for as of last night. So make sure to check that out. And that's it. We'll be back pretty much same bat time and same bat channel next week.
Well, yeah, don't miss Sarah. That's a good catch right there.
Yeah. Thanks, everyone. Have a great day.
Thank you.
Thanks, Cary.
Mhm.
Bye.
You're welcome. Bye-bye.